It's starting now our questions. At the moment, I don't see that we have questions from the auditorium. My backstage is normally giving the questions to me, and therefore we can start the cross discussions between you here on stage. If there are specific comments, you see, Alfred, you represent Navitas, who are very special doing GaN IC technology. And so the question is to the other three gentlemen, what they plan probably to follow up doing IC technology into GaN.
Well, maybe Bodo, before we jump in there,
yeah,
please allow me two short comments.
Go
two
ahead.
questions that I picked up in the last Q&A session. I think it was 1.5 hours ago or so.
Yeah.
One question was pretty much the same. What is with monolithic integration? When is it happening? Yep. And I was actually quite surprised that most people that were there were talking about how complicated it is, that the developing ICs in that technology is not easy because there is no P-channel device and so on and so forth. Well, we have done it. And yes, there are challenges. They can be overcome. And the integration actually brings a lot of advantage that is really beneficial for the application. And the other question that I remember from that Q&A session was what happens in fast switching applications when you have voltage overshoots at the switching node and consequently overcharging the bootstrap capacitor. And this is, I think, an excellent question, an excellent problem that really relates to most classical gate driver designs with bootstrap supply for the high side, but for gallium nitride, when the driver is integrated, like in our case, with a voltage regulator, then this problem simply doesn't exist because the voltage regulator will take care of it. And as a result, you can actually work with a very loosely regulated supply voltage and still have excellent repeatable performance and reliability. So those two questions I found pretty intriguing. And maybe that's a topic that could be expanded a little bit further in your magazine.
Alfred, it's great, and I'm looking forward to have these in a contributed version for the printed magazine.
My old habit of talking myself into action items.
We have every month a good magazine, so you are not in a rush.
Thank you.
Yeah, I just want to make a comment regarding NexGen. I mean, we are sort of what I call newcomers. I mean, although NexGen and vertical GaN has been around for over 10 to 15 years in making in universities and in the industry. It's sort of a extension of the technologies in silicon carbide and gallium nitride on silicon, sort of an extension, the next evolution. I mean, the devices, what we call sort of the holy grail of the power semiconductors. I mean, it's not that easy to make. It has all the other issues that you have been talking about. We have solved some of them, but in terms of driving it, having dedicated drivers, monolithic drivers, you need to sort of think about how you're going to do the switching, fast switching. We have demonstrated up to 10 plus megahertz switching. The question is it going to be useful? Can the people and systems use such a fast switching in terms of switching losses and all those things. So those are the challenges. But I think doing integrated drivers, or at least drivers in a chip, to make sure that it's specific for the transist is very important. You cannot take off-the-shelf drivers to drive devices at these high frequencies. And that's something that people need to think about. Putting devices or drivers on GaN. I mean, of course, Navitas and other people are talking about it. The question is, do you want to use expensive real estate? I mean, GaN on silicon substrates are a lot cheaper than GaN on GaN substrates. So our real estate is super expensive. So you want to make sure that you optimize the real estate for what you get bang for the buck, and it's a sort of a trade-off. For us, I mean, we can make P-channel devices, we can make N-channel devices on our substrates. I mean, we actually have P plus and P-type on the same substrates at N, so that's not an issue for us. But again, just a matter of whether you can get a good driver and whether it's cost effective. That's something that we need to sort of work on, develop. But the fact that you have to put a driver or a controller close to the GaN chip, I think everybody in the industry agrees, and sort of to get sort of the best utilization of that, the performance of devices, you have to sort of work hand in hand. You can't just give a device without how to drive it or how to operate it and expect it to perform to the best of its capability.
Very true.
Thank you.
So are we doing an introduction slightly here? Or what did you want? Can I just say a few words here?
If you want, you can start, Philip.
Okay, so I think there's a place for innovation. I think there's a place for integration, and I think there's a place for discrete. We're talking about multi-billion-dollar markets here, and markets that haven't even been, discovered. We are definitely adding markets that silicon isn't really involved with today with GaN and its bidirectional current capability. We're a discrete house. We're a discrete house, but we do work with. We do have one of our strategies is partnerships, and what we do is we actually work with IC houses. So we are focused on discrete. We can work with partners on integrated solutions, and being agnostic to drivers is an important part of one of our value propositions to our customers, with the drive and the ease of drive and designability of our technology. This is where it comes down kind of to the innovation of per my presentation, offering innovation to customers, right? So whether it's integration, whether it's a discrete solution, whether it's packaging, we offer, we're involved in the first GaN 3 kVA data center UPS. It has an internal lithium-ion battery in a form factor of 1U, where we're driving our TO247 device at 400 kilohertz, right? And with a 2.5 times reduction in size with silicon predecessor. So, I think there's advantages and there's opportunities for all of us to play and for all of us to be successful in this market. It just, it really comes down to continuing to innovate to support our customers as they evolve and grow into their businesses. Because in my experience, customers they look at your profile, your product portfolio, and they go, you have some great devices here, but it's not a very big portfolio. And what are you doing into the future? Because they don't necessarily want to hitch their wagon to something that is just a kind of a one-time, here today and gone tomorrow. So I think, as ourselves and other GaN suppliers, continuing to drive this technology forward through innovation, whether it's discrete, integration, monolithic, hybrid, there's so many opportunities, low power, high power, that, we're just touching the surface at this point. Thanks.
Thank you, Philip.
I think maybe I was at my statement here, Oliver Häberlen speaking.
Go
I
ahead.
just want to support Philip in his judgment. If we talk about integration, we have to make the difference. What do we want to integrate and what is the best partitioning? I mean, we have seen the fantastic Navitas devices out with monolithic integration of all driver components, level shifters, everything onto one die, still having separate 2-die solution for low and high side. But at the end, you pay pretty expensive real estate on the GAN part. So you might want to think about what functions do you really need to integrate onto the GAN because you want to achieve the good performance, low dead time. On the other hand, you want to keep everything on silicon that can be done in silicon because it will remain the cheaper part for a pretty long time. And this is important depending on the power levels, on the requirements. We have a full scale of possibilities from package integration to partly monolithic integration to full monolithic integration of power stages.
Mm-hmm.
Okay, gentlemen, we have a question coming in. It's addressed. Can you guys comment on the integrated UVLO threshold value dispersion impact due to the fabrication corners dispersion? Does a good design necessarily need to have very high yield, fabrication efficiency or not? UVLO. I hate the shortened, but you may know more than I.
I can maybe comment briefly on this one.
Okay.
UVLO is under voltage lockout. And,
okay, that's what I had in mind, but sometimes,
yeah,
thank you,
this
Alfred.
means that the driver turns itself off when the supply voltage is not high enough to turn the power switch fully on, at which point it may not leave linear mode and actually dissipate a lot of power and explode. So that is a feature that has been around for many, many years in gate driver design. If I may add a short comment for the Navitas components, that's not a concern because our gate driver performs the regulation precisely to the value needed by the device. And so the under voltage lockout level, if it varies, is of no concern to us. This has no impact on the real voltage that the gate is of our switching device is seeing.
Thank you, Alfred. And any more comment from the other gentlemen on stage? We are waiting for the next upcoming question. Well, somebody of you can even add his comment to Alfred's statement at the moment.
Well, the comment from Oliver was actually very true. There is no precise voltage reference in gallium nitride monolithically integrated available. So that question makes a lot of sense. And that's where you have to put, let's say, protections in other places.
Yeah,
Absolutely.
our devices are JFET, so it operates differently.
Yeah.
So I mean, you can't sort of, as I said, you can't just categorize everything under one. When they talk about GAN, I mean, GAN operates very differently than GAN JFET. So, and again, it depends on what I said, the driver design and how you sort of integrate the entire transistor with the subcomponents of the system, the gate drivers and other stuff.
Being that we're we're driving a low voltage MOSFET in our cascode structure, we're using standard drivers with standard UVLO. So this is a silicon light type drive. So no issue here.
Yeah.
It's always important that the people know that you have a cascode design and certain some people did not realize that, and it's good to know. Okay, gentlemen, maybe you have questions across yourself to discuss a little bit.
I would like to ask sort of the panel. I mean, I'm coming from vertical GaN. Of course, we talk about the higher voltages in terms of up and GaN. Do you see GaN on silicon technologies moving up in terms of going to 800, 1200 and higher voltages in your roadmaps? That's something we're looking at as well, sort of competing with silicon carbide, or that's, I know Transphorm has published some papers. Is that sort of the area that you think it's area for GaN and GaN and silicon and GaN on GaN to compete with silicon carbide?
Yeah, you know, I can take this one, Bodo. Thanks, Shen, for the question. I think it's great. Yeah, so you know, we've demonstrated 1200 volt technology. Now we're not GaN on silicon with this technology. We're actually GaN on sapphire. Right, so we can then, if we want to, we can drive that technology up higher than 1200 volts. That's kind of where we see the market for us, 650 to 1200. And that gives us the ability to basically get into what we're also looking at is the automotive sector, right? The 800 volt automotive sector, 2025 and beyond, you know, we're hearing 70% of the automobiles are going to be using 800 volt, right? And then even though we do offer 900 volt technology, you know, it's not enough, right? So the 1200 volt technology that we've developed is actually based on our previous Gen 3 technology with a sapphire substrate. And it's showing similar performance to our 650 super GaN technology. So it's higher performing than the 1200 volt silicon carbide today. So yeah, we see not only in automotive, but also in the industrial space, 3-phase applications. Now that market industrially isn't as big as the 650 volt single phase, right? But when you throw the EVs in there, you throw the charging stations, you throw the infrastructure in there, that market becomes very, very large. And it's OBC, it's DC to DC, and it's also the inverter, right? So I think this is a great opportunity for GaN at 1200 volts. Yes.
In that case, Philip, if you talk about 1200 volt, you in general have to consider the avalanche capability of normal MOSFETs, which you have not at that point. So you define at 70% the rated voltage.
Right.
That's what I learned over the last years. 60 to 70% of the maximum possible breakdown voltage is rated to overcome the disadvantage having no avalanche capability, like
Correct.
the MOSFETs can give you.
Right. So with our 1200 volt technology, we've actually demonstrated 1500 volt breakdown capability with that device. And not only that is, we have also shown a short circuit current with hold time of 3 microseconds with another technology that we've actually demonstrated. So pairing that with 1200 volts not only gives you the transient voltage of 1500 volts, but it also can give you variable from, you know, we can adjust that short circuit with hold time from, 0.2, 0.3 microseconds all the way up to, up to 3 microseconds. Pairing that with a off-the-shelf driver with desaturation protection gives you, then you have awesome protection, right? You have it from the driver, you have it from the GaN device, and you have it from the breakdown of the technology. So that is the direction that we're going with respect to, and that's some needed by EV, especially on the inverter side for traction. Some require, some want, some don't necessarily care, but this is something that we can offer. And not only that, is we can offer all this enhancement or innovation into our 650 volt technology as well.
Thank you, Philip.
Mm-hmm.
Do we have a question? Not at the moment. My backstage says the auditoriums is not bringing questions up. They are all in the coffee break in the afternoon here in Europe.
Espresso, yeah.
Or a cup of tea.
Yeah, or tea.
Tea time.
I have another sort of comment question. I think again, I guess I'm the one who's
Go
asking
ahead.
the question. Yeah, in terms of GaN and silicon and manufacturing, I mean, Infineon has, I mean, as you know, is pushing and coming up with cool GaN, and they have their own internal facilities. How do you think outsourcing versus insourcing is going to play in the market? I know sort of Transphorm sort of has a partner in Japan, Singapore, and Navitas uses Taiwan. So is that going to play in terms of innovation, play a role versus having your own fab versus not having your own fab, or it's going to become very generic?
That question is addressed to Oliver, but let me make some comments. I heard that Infineon had made quite a bit of investment in Austria as well, in Dresden. And my past experience when I was younger and worked for RCA, GE, and finally Harris for IGBT manufacturing and development was in Mountaintop, Pennsylvania, and it was always a good thing to have the engineers from chip design and from manufacturing in a close loop together to get the most efficient device manufactured. And so already in the mid of the 80s, the IGBT was still called COMFET. The 500 volt device came up with typical 1.4 volt saturation, and some of the other manufacturers had a long way to get similar good VSATs. But the one thing what I had seen from my application marketing viewpoint in Europe was that the engineering group was sitting together and the fab was next to them to make it happen. That's just something. Oliver may now make his comments to your question. It was just an old man, his comment. You
yeah,
see,
thanks, Bodo, for giving your view here. Yeah,
I'm for half a century in electronic business. That's quite a bit.
yeah, I cannot compete with that long experience, but it's approaching 30 years now in semiconductor industry. And I can confirm here that, I mean, when you talk about what's the value of having the complete manufacturing chain in one hand is, of course, the supply security that we can better plan. But on the other hand, like you pointed out, establishing a new material system, you need to have a close link between the manufacturing, device design, process development, and reliability to learn about all the possible shortcomings of the material and have short learning cycles in debugging such a new material system. So I would say that is definitely something where having the full value chain in-house, starting from the growth of the material through processing, through testing, qualification, and everything definitely helps.
Oliver, nevertheless, we nowadays have the modern communication that was not given in the mid-80s. In the mid-80s, I remember a lot of communication was done just by phone and fax. So nowadays you can exchange data and see much more, even if you have your fab in Far East and your design in Dresden or things like this.
No, definitely. The style of working has changed, and we are getting used to doing remote development across all of the world.
Like we do
Hybrid.
conferencing like this. I remember the times when I did presentations for Harris or for GE Solid State at PCIM. I had my foils, which we put to an overhead projection device, which is totally gone. And
that doesn't exist anymore. That's true. But I'm not sad, frankly speaking.
no.
But maybe I can add a short comment with regards to that learning topic also from our side. As Shahin mentioned, yes, we are producing our devices at TSMC, and TSMC being a well-known high-volume foundry in the market, they have a lot of experience in bringing new technologies to life and to good yield and good volumes and what have you. So we are hitching a ride with them to some degree now, especially also with the new GaN technology, and they are focusing on certain devices that they are making and optimizing, and they're doing that very well, adding all the capacity that we need, which has brought us to being the #1 in the gallium nitride market worldwide, surprisingly so, I should say. But the process extensions, the new devices, the circuits that we are making using that technology, that we do our own, and we are working on qualifying that our own. Now that relieves the problem a little bit, because the complicated stuff, you know, the high voltages, the high currents, and all that, which happen in the power devices, are not happening in the analog circuitry, fortunately. And so the reliability risk with going that two-phase approach, let's say in parallel, is actually very small. And we have not seen any reliability related issues with our devices in that context and in that respect. So for us, that approach going foundry is working very well. Obviously, at some point when volumes get bigger, and when I look at all the market research companies that are forecasting fantastic growth rates for the next 10, 20 years or something like that, it's actually very hard to believe those numbers in some cases. Then I think inevitably there will be a point where it might make sense for us to establish our own manufacturing facility. But this is just me thinking here out loud. We will see what the future brings.
Thank you, Alfred. We are at the end of our discussion. I will thank you all for making it to a fruitful, great thing, and I wish to all of you a nice Christmas time and a happy New Year. We have also to hope that peace in this world will soon come back to a point that life gets a little bit less stressful. So thank you, stay healthy, and looking forward seeing you at APEC or PCIM the next time. Goodbye, friends.
Thank you very much.